IR sensor. The infrared sensor is an alternative for combustible gas measurements when there is no oxygen present, or for measuring high concentrations of carbon dioxide. Infrared sensors work on the principle of light absorption. Every gas absorbs light in a particular way. Flammable gases and vapors are mostly hydrocarbons, and hydrocarbons absorb different light waves than the main components of air: oxygen, nitrogen, and argon. This distinction can be exploited to measure the amount of hydrocarbons that are present. To help you better understand what is actually happening in the infrared sensor, here is an animation to demonstrate the process. The gas to be measured enters the sensor chamber through the flame arrestor. The flame arrestor prevents any energy from within the sensor from getting back out to the atmosphere. The infrared transmitter produces broadband radiation that passes through a window into the cuvette, where it is reflected off the mirrored walls and passes through another window, falling onto the double detector. This double detector consists of a measuring and a reference detector. As illustrated in the upper right-hand corner, if the gas entering the sensor chamber contains hydrocarbons, then some of the radiation is absorbed before it reaches the measuring detector. The amount of radiation reaching the measuring detector is shown by the green bar. The more hydrocarbons that are present in the sensor chamber, the higher the reduction in the amount of radiation reaching the measuring detector. The amount of radiation that reaches the measuring detector is inversely proportional to the amount of hydrocarbons that are present in the sensor chamber, meaning that a higher output from the measuring detector represents a lower concentration of hydrocarbons in the sensor chamber. The signal from the reference detector remains unchanged. Dirt on the mirror and windows, and interference from dust or aerosols in the ambient air have the same effect on both detectors and are fully compensated. Let's review this process again by looking at this diagram. As you can see, the IR sensor has a light source inside, which projects light onto the mirrored walls of the sensor. The light waves bounce around and are measured by a double detector. One of the detectors has a filter on it that filters out all of the light, except for the infrared wavelengths that are typically absorbed by hydrocarbons. The other detector lets all of the light through and is used as a reference point to compensate for environmental conditions like humidity and dust. Gas enters the sensor chamber through the filter screen. If hydrocarbons are not present, the infrared light will maintain its intensity. If hydrocarbons are present in the air, then the infrared light becomes weaker. The intensity drops in relation to the concentration of the hydrocarbon, for example, methane. The double detector converts the reading from light into an electric signal that is read by the monitor. An IR-EX sensor will only detect gases that absorb IR radiation and have a CH, or carbon-hydrogen bond. Hydrogen, as an example, is not able to absorb IR radiation, and therefore is not detectable by an IR-EX sensor. This type of sensor can be found in the XAM 5600 and XAM 7000 instruments. The next type of sensor that we will talk about is the photoionization detector sensor. The photoionization detector, PID, is a specialized sensor that is known as a broad-range sensor, as it is not specific to any one gas. To help you better understand what is actually happening in the PID sensor, here is an animation to demonstrate the process. The gas to be measured enters the PID sensor chamber through the sensor membrane. The photons from the 10.6 electron-volt ultraviolet lamp break down the gas molecules to positively and negatively charged ions. These charged ions are counted by the collector electrode within the sensor and produce an output current that is measured by the instrument's electronics. A PID will measure a variety of toxic gases and a range of VOCs, volatile organic compounds, in very low concentrations from ppb, parts per billion, up to over 2,000 parts per million, depending on the gas being measured. Let's review the sensor design and detection process again by looking at this diagram. The sensor consists of a sensor housing, 2 electrodes, and an ultraviolet lamp. The ultraviolet lamp rating determines which gases will be measured by the sensor. The UV light produces the energy that is required to ionize certain gases. For the hydrocarbons, it requires a relatively high amount of energy to do this. This energy is measured in electron volts. The UV light ionizes the gases, which produces an electrical current. The strength of this current is directly proportional to the concentration of ionized molecules inside the chamber, and this makes it possible to determine the concentration of harmful substances in the air. Keep in mind that this sensor becomes important for concentrations of combustible gases that are toxic at very low levels, which are reached much faster than the concentrations needed for explosions. This type of sensor can be found in your XAM 7000 instrument. Now that we have studied the types of sensors and how they work, let's look into some of the factors that are important to the end customers. Draeger sensors offer advantages that are important to each frontline worker, foreman, supervisor, safety engineer,